So I guess that we can get started. I see people joining in. So let me start with introducing Kunal. So good morning, everyone, and welcome to Kunal Garg's PhD defense talk. So I would like to first thank the members of the committee, of the PhD committee of Kunal, Professors Bernstein, Kolmanovsky, and Ozey, for agreeing to participate and serve on this committee. Kunal has been with the Department of Aerospace Engineering in the PhD program since 2016. He joined under my supervision after finishing his undergrad studies at the Indian Institute of Technology in Bombay in India. And during his these years at Michigan, his research has evolved in the areas of constraint control and optimization, with applications in single agent and multi-agent motion planning problems for safety critical and time critical control applications. So he will be talking more about that soon in the next about an hour. And I would like also to announce that Kunal this year is the recipient of the Pierre Kambamba Award and also of the Leonor Towner Prize Award for a distinguished academic achievement, which I feel that there are two very well-deserved awards. So I would like to congratulate Kunal on those two very important accomplishments. And without any further ado, Kunal, the floor is yours.
Thank you. Good morning, everyone, and good evening if you are joining from India. And thank you so much for attending this talk. The title of my thesis is Advances in the Theory of Fixed Time Stability with Application in Constraint Control and Optimization. So with that, let me talk about the common control problems that we encounter as control theorists. So there are problems that are safety critical, where we do not want our flying objects or even objects, vehicles moving on ground to collide with, let's say, people, with each other, or enter zones which we can characterize as unsafe zones. And on a more serious note, when safety fails, we can have losses of millions of dollars or even human life. So we need to take into account safety while designing control input. The other classes of problems that we encounter are time critical, where the system needs to complete a given task in a given time. Now, these deadlines can be external, as in this example where the elevator door is closing and the man has to reach the other side within a given time, or they can be internal. So this video went viral 3 years back when the Boston Dynamics robot showed how to backflip, right? And one thing that we need to observe here is that how it reaches a given pose right before it hits the ground so that it can actually maintain balance. So this is a very time critical problem where if it does not reach that particular pose, then it would fall and it might even break, right? So these two kind of constraints can together be called as spatiotemporal constraint, where spatio pertains to the state space of the system, which basically say that, well, we do not want system to go somewhere or we want it to go somewhere. So that constitutes the spatial parts. And the temporal is pertaining to the time part, where we want the system to complete something in a given time. Now, a spatiotemporal constraint in themselves are very difficult to satisfy, but it becomes more complicated when we throw in input constraints. And we know that every real world system has input bounds. So quadrotors, fixed wing aircrafts, or even rockets can only fly at a given speed and even brake at a given rate, right? So the main control objectives that we consider in this thesis are how can we guarantee safety and convergence with bounded inputs. Now, a particular instance of the problem that we consider is illustrated in this figure, where we imagine that in future, where there would be a lot of flying objects in the urban city-like environment, as shown in this figure, there would be restrictions on how these autonomous aerial systems can fly. So for example, this green zone can be thought of as a boundary which these quadrotors cannot escape. So they have to fly only in this restricted zone. And these red zones can be even further restrictions that these quadrotors are not allowed to enter these red zones. So these can be the state constraints. And the objective for, let's say, for this particular quadrotor can be that starting from this particular region, it needs to visit these blue regions in a given time sequence. So maybe it is required to reach here in 30 seconds and reach this next region in next 30 seconds, right? So what we have at hand is a multitask problem that requires satisfaction of spatiotemporal requirements. And for that, we need that each individual task must be completed in a given fixed time. All right, so this motivates the kind of problem that we are dealing with. Next, let me present what we have done to address these kind of problems. So the overarching theme of my research work is fixed time stability of continuous time systems. And we use this theory on control design side, where we explored two approaches. One is a vector field-based approach. Let me just change the pointer. So one is a vector field-based approach, and one is a quadratic program-based approach. And I'm going to focus on my talk primarily on quadratic program-based approaches. And these approaches have become very popular in last few years. And just to give you an example, this is a screenshot from Google Scholar that I took on Sunday, and it shows that in last 14 or 14 and a half months, so many papers have appeared under this search phrase, which basically says that how popular this approach, the QP-based or quadratic program-based control design, has become. And the reason for this is very simple. A lot of groups have shown that these QPs can actually be implemented on board for online control synthesis, because QPs can be solved very efficiently. So this is one of the approaches that we took when we talk about fixed time stability in control design. Now, we also worked on the optimization theory, where we design schemes that can solve optimization problems within a fixed amount of time. In particular, we dealt with two classes of problems. One is smooth problems, where the objective function that we are trying to optimize are at least once continuously differentiable, and non-smooth problems where the derivatives might not exist. Now, in our lab, as Professor Panagu mentioned, we also work on multi-agent problems, where we wish to design on the control side distributed controllers, where we can imagine, let's say we have n number of quadrotors or n number of robots, and they only have access to local information. So let's say they have a communication or sensing radius of 10 meters, 15 meters, depending upon the kind of sensors they have, and they can only use that local information while designing their controllers. So we designed distributed controller, again, using this theory of fixed time stability. And similarly, on the distributed optimization side, we explored the problem of minimizing or maximizing team objectives, where the individual nodes are only able to communicate with their neighboring nodes, which is basically depicted by the underlying communication graph. Now, in this talk, I'm only going to focus on these two topics. I'll start with our results on the quadratic program-based approaches for safety critical and time critical systems, and then I'll briefly touch upon our results on smooth optimization problem. So we were able to publish some journal papers through this research. The initial 4 papers have already been accepted or published, and there are a few which are ready to be submitted. And we were also able to publish a few number of conference papers. So with that, this is the outline of the rest of my talk. I'll start with our results on control synthesis side using quadratic programs. So I'll start with the nominal case, and then we'll briefly present our results on the robust control design side. And then I'll also present our results on the theory of fixed time stability and convex optimization. And then I'll conclude my talk with some thoughts for future work. So because I've been talking about this finite and fixed time stability, let's first see what these concepts mean. So we know from our nonlinear controls class that for asymptotic or exponentially stable system, the system trajectories reach the equilibrium point. And in this case, if we assume the origin to be the equilibrium point, asymptotically or exponentially, which is to say that they reach their equilibrium point as time tends to infinity. The concept of finite time stability, however, requires that same thing happens within a finite amount of time. So here we can see that this blue trajectory hits the origin within 0.2 seconds. So if we want to define finite time stability, we consider this nonlinear system, and let's assume that the origin is the equilibrium point. And authors of this paper cited below define finite time stability as follows. So we say that the equilibrium point of this dynamical system is finite time stable if it is Lyapunov stable, and there exists this settling time function, which can depend on the initial conditions, but it takes finite values such that as t tends to this capital T, system trajectories reach the origin. The authors also gave Lyapunov conditions to characterize the finite time stability of the system. And the main thing is essentially this highlighted inequality that the time derivative of Lyapunov function v should satisfy. And here also, we should focus on this exponent appearing on the right-hand side, which should be between 0 and 1. And the authors showed in this paper that if a Lyapunov function satisfies this kind of an inequality, then the system or the origin or the equilibrium point in general of the system would be finite time stable. And this time of convergence, or the settling time function, would have this kind of an upper bound. All right, so we have this notion of finite time stability where we know the upper bound on the time of convergence. One of the issues with this concept is that this upper bound can grow unbounded as the initial conditions go farther and farther away from the equilibrium point. So for the applications that we talked about in the motivation slides, we can use a stronger notion which we call, which is called in literature as fixed time stability. So the authors of this paper define fixed time stability as follows. So they say that an equilibrium point is fixed time stable if it is finite time stable, and in addition, if the settling time function can be uniformly bounded. So if the supremum of this function is finite for all initial condition, then the equilibrium point is called as fixed time stable. Now, just to illustrate the difference between the two notions, so the blue trajectories, or rather the norms of the trajectories, are for finite time stable system, and you can see that they hit the equilibrium point, or the origin in this case, within a finite amount of time. But this time grows as the initial conditions go farther and farther away from the origin. On the other hand, these red plots show the convergence for the fixed time stable system. And as we can see, there exists an upper bound within which the system trajectories reach the origin irrespective of where they start from. So this fixed time stability notion is a stronger notion than finite time stability. All right, so the authors also gave Lyapunov conditions to characterize fixed time stability, and these are given here. Now, again, what we need is essentially a Lyapunov function whose time derivative can satisfy this kind of an inequality along the system trajectories. And the difference from finite time stability is essentially that we have two terms now, where one of the terms still has an exponent between 0 and 1, but there's another term whose exponent is greater than 1. And what we get out of this inequality is essentially a settling time function whose upper bound is basically independent of the initial condition. So we have a uniformly bounded settling time function, and that's why we call the equilibrium to be fixed time stable. Now, again, going back to the motivating problems, what we really need is convergence to happen in a user-defined time, right? So we should be able to specify the time within which we want our systems to converge. And to do that, what we can do is we can further bound this particular expression by whatever user has given to us. So let's say if user wants the convergence to happen in 1 second, we can upper bound this, this particular expression by 1 second. And so what we can do is we can choose these parameters, alpha 1, alpha 2, gamma 1, and gamma 2, so that this kind of an inequality is satisfied, which would basically result into convergence in a user-defined time. All right. So why do we care about finite and fixed time stability? One thing is that it leads to better disturbance rejection. So it has been established that faster convergence leads to better disturbance rejection. In particular, if we have a nominal system whose equilibrium point is finite or fixed time stable, and if we perturb it on top by adding disturbance, and if this disturbance is vanishing in the sense that it satisfies this kind of an inequality, then we can show that the finite and fixed time stability of the equilibrium point would be preserved. So the equilibrium point of this perturbed system would still be finite or fixed time stable. On the other hand, if this disturbance is non-vanishing, then we can only guarantee that the trajectories converge to a neighborhood of the equilibrium point, and they cannot really reach the equilibrium point itself. But with faster convergence, we get convergence to a smaller neighborhood. So as compared to asymptotic or exponentially stable systems, for finite time stable system or fixed time stable system, the trajectories would converge to a smaller neighborhood. So in brief, we basically get better disturbance rejection. Now, we already discussed how time critical application needs convergence within a fixed amount of time. So this figure, which was given to me by one of my lab mates, Vishnu Chipre, depicts one scenario where these defenders need to capture these attackers before they enter these safe zones. So the defenders only sense these attackers once they enter this kind of a golden zone around the safe zone. And in this limited amount of time that the attackers would take for reaching from here to here, the defenders must capture them, otherwise they would lose this particular pursue evasion game, right? So that's a time critical application which needs convergence to happen within a given amount of time. And we already discussed about this real world problem where we might need completion of sequential tasks in a given time sequence. And again, this theory of finite and fixed time stability can come handy here. And I would not have time to talk about this particular aspect here in this presentation, but we also showed in one of the recent papers that I'm writing with a group at Caltech, where we showed that fixed time stable controllers are actually able to complete some time critical tasks which exponential controllers actually fail. So we get real benefits when we use these concepts. All right, so let's see the main problem statement that we consider in the control design side here. So we consider a general class of nonlinear control affine system. Control affine because the controller U appears linearly in the system dynamics. And we consider these two sets here. So the blue set, which is given as a zero sublevel set of this function HG, can be thought of as a goal set. And this green set, which is again a zero level set of a function H's, it can be thought of as a safe set. And the problem statement is given here. So what we require is to design a control input U, which should satisfy this kind of control input constraints, such that the system trajectories always lie within the safe set. So this set S subscript S should be forward invariant for the system trajectories, and they should reach this goal set within a user-defined time. So that's why we can think of this green set as safe set, because we want our trajectories to always remain inside. And we can think of this blue set as the goal set because we want the system trajectories to reach there. So basically this black trajectory is what we are seeking, and we do not allow the system trajectories to ever leave this particular green set. All right, let me talk a little bit about these input constraints. So if we have component-wise input constraints, which are very common, and let's say if we are dealing with fixed-wing aircraft or even simplified car-like model, they can be directly written down in this linear inequality form. But if we have more general constraints, so let's say for a simplified multi-rotor aircraft model, if we are modeling them using single integrator or double integrator systems, then we would generally have two norm type constraints, and we can approximate them to again get this kind of an inequality. And why do we care about this kind of an inequality? Because as I mentioned earlier, we would be formulating quadratic programs, and we can only deal with linear inequalities there. All right, so certain assumptions that we require. So we want, or rather we need that these, the intersection of these sets is non-empty so that we can indeed solve this problem. And the other technical assumptions are that these sets have non-empty interiors and that this goal set is compact so that we can guarantee global convergence. All right, so a brief literature review. As I already mentioned, there has been a lot of work on quadratic program-based control synthesis in past few years. So this is just a non-exhaustive list of some of the work, but let me point out what is missing from the literature. So these work talk about safety and convergence, but they only guarantee exponential convergence, which is something that we address in this paper, where we guarantee safety as well as fixed time convergence using quadratic programs. Now, there are some papers that talk about finite time controller also in the QP setting, but they do not consider input constraints, which is something that we address in this paper, where we guarantee that the underlying QP would be feasible while incorporating input constraints along with safety and fixed time convergence. And finally, there has been some work on disturbance consideration, but again, these work do not consider input constraint, and they only deal with exponential convergence. So this particular paper, which we are going to present in this year's ACC, talk about robust safety and fixed time convergence under input constraints. All right, so these are contributions with respect to the literature. And before jumping to the quadratic program results, let me present some new fixed time stability Lyapunov conditions that we have derived here. And to motivate why we need these new conditions, let's consider the simple problem where the system is just a one-dimensional problem. So F and G maps from R to R, and the input constraints that we have are simple box-like constraints. And the objective for the system dynamics, or rather system, is to converge to this goal set within a user-defined time. Now, a natural approach using quadratic program would be to set up this kind of a QP where we would want to minimize pointwise norm of the control input such that it satisfies this kind of control input constraints. And we can use the Lyapunov condition given by Polyakov back in 2012 so that fixed time stability can be guaranteed. Now note that this is indeed a quadratic program in U because U is the variable of optimization. And here X, which is a parameter of this optimization, can appear non-linearly, but U appears linearly in both the constraints. So this is indeed a quadratic program. And what result we can get out of this is essentially if this QP is feasible, then any solution of this QP would solve or rather satisfy this objective. But the problem is that it might not be feasible, right? Because we have input constraints and we are trying to satisfy this inequality on top of it. So what can we do about it? Well, one of the natural approaches would be to introduce a slack term in this convergence constraint, right? So with this slack term, we can guarantee that this QP would be feasible, but can we still guarantee that fixed time convergence would be achieved? So let's see if we can prove that. So that's where we get motivated for these new fixed time stability conditions. So I'm not going to read the whole theorem here, but essentially let's focus on this highlighted inequality for the Lyapunov function. So in addition to these two terms, which were already introduced in the literature, we allow another term to appear on the upper bound of time derivative. And if a Lyapunov function satisfies this kind of an inequality, then we show that there exists this domain D, which we call as domain of attraction, such that for all initial conditions in this domain, the system trajectories reach the equilibrium point within a fixed amount of time. So essentially what we get out of this condition is fixed time stability from a domain of attraction. Now I'll come back to this domain of attraction, but let's see what we get from this result first. So as we already discussed, if we use this kind of a condition, keeping this delta 1 as a free variable, we would be able to guarantee feasibility of the underlying QP. And another thing that we get out of this particular equation is robustness with respect to additive disturbance. So in brief, if the nominal system has its equilibrium point fixed time stable, and if we perturb it on top by vanishing disturbance, then we can use this condition to show that the fixed time stability would still be preserved, at least from a domain of attraction. All right, so I have been talking about this domain of attraction. Let's see how it looks like. So to characterize this domain, we first need to characterize the points where V dot takes negative values, all right? Excuse me. So for that, we rearrange these three terms on the right-hand side of V dot to get this expression. And note that V is a positive definite function. So with a negative sign outside, this term is always negative. So what we are left with to analyze is basically this term in parentheses. And we want to see if this beta function is positive or negative, which would basically dictate whether this V dot is positive or negative. Now, we show in our thesis and in papers also that if this ratio of delta with respect to these terms alpha 1 and alpha 2 is less than 1, then this beta function always takes a positive value for all possible values of x. All right. So if beta is positive with this negative term outside, we get that V dot would be always negative. All right. But things become more interesting when this ratio is greater than equal to 1. In particular, the state space gets divided into 3 disjoint sets. One is this red domain, which is a neighborhood of the equilibrium point where this beta function takes positive values. And so V dot takes negative values. Another set is this green zone, which extends to infinity, all the way to infinity. Here also, this beta function takes positive values, and again, V dot takes negative values, all right? Now, the annoying part is this blue strip between this red and green zone, where this beta actually takes negative values. And with this beta being negative and minus V of x being negative, V dot would be upper bounded by a positive value. So we do not know if V dot can actually take negative value. So we cannot say anything about V dot. And so in this particular case, the domain of attraction would only be this particular red domain where we know for a fact that V dot is negative. So using this, we get this kind of expressions for domain of attraction. So when this ratio R is less than 1, we already discussed that the whole Rn would be the domain of attraction. And when this ratio is greater than equal to 1, then this red domain, whose closed form expression is given out of this equation, would be the domain of attraction. All right. So let's get back to this one-dimensional problem and see how we can solve this problem using these new fixed time stability conditions. So again, we have this one-dimensional problem, box-like constraint, and the objective of driving the system trajectories to this goal set within this user-defined time. And what we can do is we can formulate a QP with this new fixed time stability result where we have this delta 1 times V function as the slack term here. And again, note that the optimization variables are U and delta 1, and they appear linearly in this quadratic program's constraints. So again, it is indeed a quadratic program, and it would be solved as a function of this parameter X. And what we can guarantee is that it's going to be always feasible because we have the slack variable here. But can we relate the input constraint at this time of convergence and domain of attraction, particularly for this particular quadratic program? So first, let's see if we can establish any intuitive relation between these 3 concepts. So intuitively, we know that if we have a fixed time in which we want our systems to converge, then more control authority should lead to a larger domain of attraction, right? So to illustrate this, let's assume that we have a quadrotor which is trying to reach this goal point shown via this star. And if this quadrotor can move with a maximum speed of 10 meters per second, then there would be this circular region. Let's say if we want to do it in 1 second, then the circular region would be of 10-meter radius. And starting from anywhere in this region, the quadrotor would be able to complete this task. But if we have a larger control authority, let's say a quadrotor with maximum speed of 20 meters per second, then there would be a larger domain, starting from which the quadrotor would be able to achieve the same task in 1 second. All right, so basically more control authority would imply larger domain of attraction. Similarly, if we fix the control authority, so if we fix the maximum speed by which things can move, then larger time in which we want our system to converge should imply larger domain of attraction, right? To again illustrate this, let's consider the same example where now we want this quadrotor to reach this particular start point within 1 second. And for a given speed, we can again find this kind of a circular region starting from which the quadrotor would be able to complete this task. Now, if we allow the quadrotor to complete this task within 2 seconds, then there would be a larger domain starting from which it would be able to complete the same task, right? So essentially, more control authority or larger time requirement would lead to completion of tasks starting from a larger domain of attraction, right? So that is intuitive. Now, let's see the quadratic program that we discussed on the last slide. Does it incorporate these intuition inherently? So to see that, what we do is we find the closed form expression for that QP using KKT conditions, particularly in the case when the control input is saturated. So I'm not going to talk about how we obtain this expression, but let's just focus on this highlighted term and restrict our discussion on this particular domain. So we want our X to be restricted in this domain because that's required for the KKT condition to hold. In particular, we want the Lagrangian multipliers to be strictly positive in this particular case. And after some manipulation, we get that this Lie derivative should be strictly negative. And similarly, we restrict our discussion to this domain because this is essentially V dot, right? And we are concerned about the domain from which trajectories converge to the equilibrium point. So let's only talk about the domain where V dot takes negative values. So when we restrict our discussion to this domain, we can see that LGV of x being negative, if we increase this term, this highlighted term becomes more and more negative, leading to this ratio becoming smaller because everything else here is positive. TUD is the time convergence requirement, and mu and pi are some positive constants, right? So if we increase u, this ratio becomes smaller. Similarly, this highlighted term here is negative because of this restriction. So again, if we increase the time requirement, because of this term being negative, again, increasing this decreases the overall ratio here, all right? So essentially what we get is increasing or increasing the time requirement decreases this ratio. Now, how does this ratio relate to domain of attraction? So for constant R, the domain of attraction that I just talked about in a few slides back can be more compactly written down in this form. But this R was basically the ratio of constant delta and alpha 1 and alpha 2. In this particular case, when this R is a function of x, we can find another expression using the supremum value of this ratio R star, denoting it as Rm, and then we get this particular expression for the domain of attraction. And to see how this value of Rm affects domain of attraction, we focus on this figure. So when Rm is 1, or in this particular example, it's small, we get a larger domain of attraction. So the whole domain bounded by this blue circle is our domain of attraction. And as we increase R, we see that this circle becomes smaller and smaller. So we get a smaller and smaller domain of attraction. Now, we already established in the previous slide that if we increase or we provide more control authority to the system, or if we increase TUD or allow system to converge in a longer time, then that decreases our star, and that would inherently decrease the maximum value of Rm. And so again, we get that increasing control authority or providing more time can lead to decrement in the, in increment in the domain of attraction. So that basically matches the intuition. All right, so let's get back to the main problem, the quadratic program-based control synthesis. So just to recall, this was the problem that we were considering, a control-affine system with objective of remaining inside the safe set at all times and reaching the goal set within a user-defined time. To address that, we proposed this quadratic program where, again, the variables of the optimization are u, delta 1, and delta 2, which appear linearly. So it is indeed a quadratic program, and the individual constraints have these meanings. The first constraint highlighted in light blue is the input constraint, and we talked in detail about why we care about these being linear. The second constraint in brown is the new fixed time stability condition for the goal set SG. And this light green constraint is required for the forward invariance of set S subscript S. So with these three constraints, we can guarantee that convergence and safety would be achieved with input constraint. And because we are using these flag variables here, we can guarantee that this particular QP would be always feasible, at least when we are not hitting the boundaries of these sets. And we already talked how this variable delta 1 in comparison to this fixed values of alpha 1 and alpha 2 dictate the domain of attraction from which we can guarantee fixed time stability. Now, under this technical condition of strict complementary slackness on this QP, we can also guarantee that the solution of this QP would be continuous function of the parameter X. And why do we care about continuity? So here we are talking about forward invariance of set SS. And in this work, we are using Nagumo's theorem, which required that the system trajectories are uniquely determined in forward time. So what we show in our paper is that if this particular slack variable takes finite values, then even with the solution of the QP being continuous, the closed loop solution would exist and would be uniquely determined. And this is a strong result because in prior literature, when people are using quadratic programs, they actually enforce a stricter condition where they require that the solution of the QP is at least locally Lipschitz. And that requires even more restricted conditions on these functions and the system dynamics. In this work, we show that the same thing can be guaranteed only with continuous control input. And so we basically relax those assumptions here. All right, with that, this theorem presents the main result for this QP. And again, I'm not going to talk about all the technical details here, but in brief, what we show is that safety or forward invariance of this safe set SS is always guaranteed. So irrespective of what the value of this slack variable is, we can always guarantee that the set SS is forward invariant. But for convergence, we can only guarantee convergence depending upon different cases. So when the maximum value of this ratio denoted as Rm is less than 1, then we already talked that the domain of attraction would be whole state space Rn. And so for this problem, phase-time stability would be guaranteed for any point inside this safe set. When this ratio is greater than 1, then we already mentioned that there would exist a domain of attraction around this set as the equilibrium point, but in this case, it's this goal set as G. And so because we are concerned about safety also, we can take the intersection of this set D with set SS, get this brown set here, which we denote as DS. And so we can guarantee that fixed time stability along with safety would be guaranteed if we start anywhere inside this domain DS. So that's the main result of this particular quadratic program. All right, so, sorry. Oh, I thought I heard something. All right, so let's see one simple case study to see how this QP work in practice. So for this case study, we consider a two-agent problem and we model them using simple single integrator dynamics. And their objectives are listed here in signal temporal logic. And I'm not going to go in details of what these objective means, but in very brief, this G notation encodes the safety requirement. And in this particular example, the safety is encoded as follows. So we want our agents to always remain inside this blue zone, which if you can relate back to that figure that I talked earlier, it was that green zone in that figure, right? So this is the blue zone in which we want our quadrotor or the moving agent to remain inside. And this red zone is where we do not want our quadrotor or the agent to enter. So essentially, this is the space where it can evolve. And these F functions encode convergence within a fixed time. So what we need is for agent 1, starting from this set C1, we want that it should reach to the set C2 within a given amount of time T1, then to C3, C4, come back to C1 while satisfying the safety constraint at all times. And similarly, agent 2, starting from set C3, it should visit set C2, C1, C4, come back to C3, while again satisfying the similar safety constraint. On top of it, we want that these agents should maintain a minimum distance with each other. So if we imagine that these two agents are quadrotors, then they should not collide, right? So they should maintain a minimum distance with respect to each other. And here we consider that their control inputs are two norm-bounded. All right, to solve this problem, what we do is we construct some intermediate set and divide the problem into even further steps. So for agent 1, starting somewhere here, we require that the agent first reach its set S2, then S3, and so on and so forth, so that it can complete the sequential task. And similarly, for agent 2, starting in this set S5 bar, they should reach to set S4, S3, and so on and so forth. All right, so this is the simulation video, and we would see that the agents complete their task, and whenever they meet, they resolve their conflict. So they maintain a safe distance, and they keep completing their task within the given time. Again, they maintain safety, and they finally reach their destination. And this plot here shows the control input for the two agents, and as we can see, the control input converges to 0 in less than 1 second. So the time requirements for each individual task was 1 second, and control input converging to 0 in less than 1 second basically say that the agents were able to complete their task long before the required time. And this plot here shows the interagent distance x1 minus x2, and the red dotted line is the minimum required distance. And as we can see, the blue line is always above the red line, which basically shows that the agents were maintaining safety when they met in these two zones. So we had that the agents satisfied all the constraints and they completed their tasks. All right, so let's see how we can consider some robustness consideration in this QP-based framework. So for that, we add an additive disturbance on top of the nominal dynamics, and we assume that we do not know what this D function looks like. We only know an upper bound on this D, which we denote as gamma. In addition, we also assume that we do not know the state perfectly. So X, which we are going to use, or rather which we generally use for control design, we assume that it's not available to us perfectly, but only an estimate denoted as X hat is available. And the mismatch between these two is upper bounded by epsilon. So we assume that we only know epsilon and gamma here. Now in this particular problem formulation, we also introduce a time varying set, or what we can call as a dynamically changing safe set. And what it models essentially is moving obstacles or other agents in the environment that can be present in a multi-agent scenario, all right? So if we imagine that there are n number of agents whose states are denoted as xi and xj, and if agent I is supposed to maintain a safety with respect to all the other agents dictated by this function h as a function of xi and xj, then this being less than equal to 0 basically would lead to a time varying set. A particular instance of this would be when xi and xj are the positions of these agents, and if we want to maintain a safe distance, as we saw in this earlier example. So if we want to encode safety in that respect, then if we can choose the function h to have this form. And if we want to encode all those safeties in one particular function, we can use this approximation called as log sum x approximation to basically encode all those safety requirements in one function. We can also incorporate all the safety requirements separately also in the quadratic program. But let me just present the result for the case when we actually use the approximation. So for that, this is the quadratic program that we use. So we formulate a QP where the variables are again u, delta 1, delta 2, and delta 3, which appear linearly. So it's a quadratic program, and the parameter in this case is x hat. So as we already discussed, we do not know x, but we only know x hat, right? So we use that as the parameter of optimization so that the controller that we get out of this QP would be a function of x hat. And the meaning of this constraints are similar: input constraint, fixed time stability condition for set SG, forward invariance for the set SS, and for the set ST. Now, instead of using just the function HGs, we are using these head functions, which are defined here. And the logic behind defining all these things and introducing these new terms is as follows. So these additional terms corresponding to gamma incorporate robustness with respect to the disturbance D. So this D disturbance is upper bounded by gamma. So we introduce these three terms in the constraints of the QP themselves to account for the disturbance D. And in the definition of these functions, or the head functions, we introduce these terms corresponding to epsilon, which was the maximum state estimation error. So these highlighted terms below account for the state estimation error. And finally, this partial time derivative of function h with respect to time encodes other agents' effect on agent I's safety requirement in a multi-agent setting. All right, so with that, let's see another case study. And in this case study, we simulate underactuated underwater autonomous vehicle. So the dynamics is a little bit more involved than just the simple single integrator dynamics. And here, the control inputs are the force along the x-axis and the torque along the yaw axis. And we also consider water currents as the additive disturbance that affect the motion of these agents. And we assume that we do not know the speed or the direction of the water current, but only an upper bound on these disturbances. And naturally, we consider input bounds and that the state vector is not available to us perfectly. Now, the objective for these underwater vehicle that is shown in a zoomed view here are as follows. So we require that each agent converge to their respective goal regions within a user-defined time. We also consider field of view for each agent, which is shown in green for this agent, which is basically given as a function of this radius r and this angle alpha. And the objective here is to keep a point of interest in its field of view. So we can imagine that there's something that this underwater vehicle is tracking, and it should always keep this point pi in its field of view. And we also consider safety. So these agents should be able to maintain a safe distance with respect to each other. All right, so here we consider a 4-agent scenario, and I'm only showing the field of view for one of the agents because otherwise the video becomes too crowded. But you can imagine that each agent, they have their own individual field of views. So this is robust multi-agent control using QPs, and the objectives are as follows: maintaining safety with other agents, keeping the point of view in the field of interest, point of interest and field of view, sorry, and reaching the goal location. So the point of interest are shown in these square dots, and you would see that this agent 2 always keeps this square dot in its field of view. And the goal locations are shown in this circular regions. And one thing that we would notice is as these agents come closer and closer, they would actually not collide. They would again resolve their conflict, maintain a safe distance, and eventually reach their respective goal locations. And we also had the water currents, which I cannot really show in this video, but there were those disturbance present. So as we can see, they reached their goal location, they maintained the safety, and they always kept their respective point of interest in their field of views. Which is something that's depicted from this particular figure also. And let me try to pause this video. Never mind. So this particular plot shows the maximum values of the individual barrier functions. And the maximum value being negative basically shows that all the safety constraints were satisfied. Here we considered 3 cases. One was the nominal case where we did not consider any disturbance. One was the case where we only considered state estimation error, and the red case was when we considered both the additive disturbance and the state estimation error. And in all the 3 cases, we can see that the maximum value of barrier function was always negative, which means the safety was always maintained. All right, so that wraps up our discussion on the control side. Let's see what we have done on the fixed time stability and convex optimization topic. So to motivate why we are studying fixed time stability and continuous time optimization, there has been a lot of work in recent years as well as in past also on fast schemes to solve optimization problem, because they are going to enable online controllers synthesis using the optimization problems that we just saw. So like if we want to implement those QPs on board, then we really want that those QPs can be solved efficiently and very fast, right? Now, in this work, we study OD perspective of the optimization, and these ODs offer useful insights into the optimization theory. And we know that the optimization problems are generally solved using iterative methods in discrete time. So why do we care about continuous time optimization? Well, from theoretical perspective, I mean, it gives insights on how the optimization algorithms behave. But in the continuous domain, we can also obtain simple proofs using the Lyapunov theory. Just to give you an idea, this is the analysis that Boyd's book on convex optimization does on accelerated Newton's method. And I'm not saying that this is a bad proof, because it's a very, very nice proof, but I mean, it's just so complicated that it requires 4 pages of a book to complete the analysis and to show that Newton's method is indeed accelerated. On the other hand, if we want to replicate the same proof in continuous time, all we need is a Lyapunov function and its time derivative to have this kind of a bound. And we can very easily complete the proof within a few lines of algebra. So what I'm trying to say here is that continuous time methods might not be very useful from practical perspective, but they give useful insight and the proofs become very, very simple here. All right, so it's not that we are the only ones who are working on the continuous time. There has been a lot of people who have started working on continuous time optimization, particularly accelerated schemes in continuous time. In recent years, we have also seen some work on finite time stability in the domain of optimization, but most of the work either only guarantees finite time convergence or they assume very strong requirements on the objective function. So our contributions are, first, we guarantee fixed time convergence, which, as we already discussed, is a much stronger notion than finite time convergence. We relax assumptions on the objective functions, as I'm going to discuss in next slides, and we also cater min-max problems. So not only just minimization problem, but problems which require minimization as well as maximization. All right, so first, let me talk about unconstrained optimization problems. So unconstrained optimization problems can be formulated very simply. So we have a function f, and we want to minimize it over all possible values of x, right? So we make some assumptions on this problem. First thing, we assume that the minimizer is unique. And we want this assumption so that we can design globally convergent methods. Second, as I already mentioned, we relax the assumption. And the relaxed assumption that we use is satisfaction of this PL inequality, which was shown in this paper that it's relaxation of the most common assumption used in the literature, which is one of the most common assumption is strong convexity. And in particular, this paper showed that every strongly convex function satisfies PL inequality. So basically, it is more general than strong convexity, but it's even more general. So we do not even require convexity for a function to satisfy PL inequality. So when we say PL inequality, is basically satisfaction of this kind of an inequality, all right? And this figure shows an example of an invex function whose equation is given here, which is not a convex function, but it still satisfies PL inequality. So that's how general this assumption is. All right. So some important example that indeed satisfy PL inequalities are given below here. So whenever we are dealing with least squares problems or SVM problems in machine learning, we generally encounter these functions. And when this matrix A, which we can construct out of these vectors also, if it is full rank, then we can show that even these functions would be strongly convex. But if this matrix is not full rank, then this function f would not be strongly convex, but it would still satisfy PL inequality. So in this particular framework, we can solve the problems involving these functions even when this matrix A is not full rank. All right, so in the interest of time, let me just briefly present our results here. So what we do is we modify the gradient flow by introducing these two terms where one of the exponent is between 0 and 1, and the other exponent, because it's appearing in denominator, it's less than 0. And with these two terms, what we show is that under PL inequality assumption, the trajectories of this dynamical system converge to the optimal point globally within a fixed amount of time. Now, these results can be extended to other setting of assumptions also. So if we are dealing with strictly convex functions, then we can modify this gradient flow and introduce this inverse of the Hessian. And we can again show that trajectories of this system converge to the optimal point x star within a fixed amount of time. This plot shows how the trajectories of the modified flows look like. So we consider an instance of an SVM problem with 500 points. And the nominal case, which was the nominal scheme that was used in literature, on this log plot has a linear convergence, which is what literature has shown also, right? That this would have linear convergence. On the other hand, our scheme, irrespective of the initial condition, always converges on and before this theoretically predicted time. So it shows that the scheme actually has fixed time convergence. But we can also see that it has superlinear convergence because on this log plot, it has this curvilinear convergence, as we can see here. So essentially, we have far better performance as compared to the schemes that are nominally used. Now, let me very briefly talk about min-max problems. So as compared to minimization problems, min-max problem require that we minimize a function over one set of variables and maximize it over another set of variables. So in a 2D, we can imagine that we are trying to find a saddle point where we are minimizing it along this axis and maximizing it along this axis, all right? So we are trying to essentially find a saddle point of this function. And even constraint optimization problem have one-to-one relation with these min-max problems. So if we are dealing with optimization problem with equality constraint, we can equivalently write them in this form, which is essentially a min-max problem. But in more general setting, these min-max problems are very, very common, either in machine learning setups or even in pursue evasion games, right? So we can model the zero-sum games as minimization for one agent and maximization for another agent, right? So these are very important class of problems. And as I mentioned, that what we are trying to find is a saddle point. And so the dynamics that solve for these problems are naturally called as saddle point dynamics. And the nominal dynamics, which has been introduced in literature in past, looks like this. So under certain assumptions on the function f, people have shown that this nominal dynamics would have asymptotic or exponential convergence. So what we do is essentially, again, modify this nominal dynamics so that we can guarantee fixed time convergence. And I'm not going to go into detail, but essentially under strict convexity, concavity assumption, we use this Newton's-like flow where we use the Hessian inverse, and we can present the results in various different settings also. So let me present more numerical case studies here. So here we want to maximize this function given here. And in this simulation example, we consider different time steps. So all the numerical examples shown in this slides are simulated using Euler discretization. So basically we use a fixed time step. And we did this particular case study with different time steps. And what we can see from this plot is, irrespective of the time step that we chose, the scheme always converges within a given time. And even the superlinear nature of the convergence is preserved independently of the time step, which is a very strong observation. I mean, we did not prove it, but that's something that we observed. We also studied the effect of these exponents that I mentioned in the scheme. And when we choose gamma 1 and gamma 2 to be 0, we obtain back the nominal saddle point dynamics, and we see here that it indeed has a linear convergence. And as these gamma 1 and gamma 2 go away and away from the 0, we get faster and faster convergence here. As we can see that as the color shift from blue to red, the convergence become more and more superlinear, and it takes less and less time. So essentially, we actually get faster convergence due to these exponents. All right, so I talked a little bit about what we observed via discretization in the simulation, but let's see if we can actually provide some sort of theoretical guarantees. And this is something that we did not really study in the thesis, because that's something that I've started exploring very recently. So I'm going to very, very briefly talk about it. Now, in the continuous time, we are dealing with dynamical system of this form. And if we want to discretize it, what we are seeking is a function capital F that can basically model the discretization of this scheme. And the big question is, if the continuous time system has its equilibrium point finite or fixed time stable, can we discretize them in a manner such that the discretized system would have what we can call as fixed number of step convergence, all right? And it's not something that we have started thinking about. A lot of people have already started working on this problem, particularly this paper here listed below talk about what they call as consistent discretization, all right? So they propose this scheme which is implicit in nature. So xk plus 1, which is what we are trying to find given an xk, appears on both sides of the equation. So it's an implicit scheme. But under the assumption of homogeneity, they show that this particular discretized scheme would have exact convergence to the equilibrium point. So that's why they call it consistent discretization, because the convergence nature is consistent, being finite time. Now, when the original dynamical system was fixed time stable, the same scheme converges to an arbitrarily small neighborhood of the equilibrium point within a fixed number of steps. So that's what was shown in this particular paper, all right? But the problem is that it is implicit and assumes something called as homogeneity, right? So can we do better? So this in this paper, Dr. Ben Osman shows that something better can actually be done. And the better thing there is essentially just using simple Euler discretization. And he shows that this simple discretization, which is very easy to implement, which is what we implemented in our simulations also, without any additional assumption on F, actually converges to an arbitrarily small neighborhood of the equilibrium point if the original system was finite time stable. And that convergence happens within a finite number of steps. And that number of steps are dependent on X naught, all right? So they studied in this paper finite time stable systems. Now, we also proposed some preliminary results, or rather we are working on these preliminary results in collaboration with the people mentioned below, where we consider dynamical system whose equilibrium point is fixed time stable. So we assume that there exists T subscript fxts such that the system trajectories converge to the origin assumed to be the equilibrium point in this case within this time. And we seek results for this kind of an Euler discretization. And we have been able to prove that for any epsilon, where epsilon dictates as to how closely we want the trajectories of these two systems to remain, and for every time capital T, which dictates for how long we want this closeness to happen, we can find a discretization step H star such that as long as this discretization H is smaller than H star, this would be guaranteed. So, I mean, in brief, what we are saying is that for every epsilon, where epsilon dictates where we want our system trajectories to converge, there exists an H star discretization step such that if we choose our discretization step smaller than that, then the trajectories of the discretized system converge to this arbitrarily chosen epsilon within a fixed number of steps that is independent of the initial condition. So that is a very strong result that we have shown very recently. All right, so with that, I'm happy to conclude my talk, and let me talk briefly about the conclusions of the control design part. So we showed new fixed time stability condition, which were instrumental in proving feasibility of the QP, even with input constraints. We established relation between the domain of attraction, input constraints, and time of convergence. And we use these results in a quadratic program-based formulation, guaranteeing safety as well as fixed time convergence. And we also considered a multi-agent robust control design problem, again, using the same QP framework. Now we have some recent developments on the topic. So one of the requirements that I briefly touched upon was the continuity requirement on the solution of the QP. We mentioned that we relaxed the assumption that were already there in literature, but it still requires certain assumptions, right, to be able to guarantee continuity. In this paper, in a paper that I wrote with James in our lab, we show that even the continuity requirement can be relaxed, and we can leverage non-smooth analysis theory to not require any regularity requirement on the solution of the QP, and still we can guarantee forward invariance. Now, the other problem with these QP-based methods that I just talked about is related to implementation. So we mentioned that the X, the state was the parameter, and we want to solve this QP for each value of X, right? Which is impractical because we cannot solve QP continuously. So to address that, we study very recently, again, in collaboration with one of my lab mates, Joseph, zero-order hold control, where we basically compute a control input, keep it constant for our time step, and we show how we can guarantee safety even with these kind of piecewise constant control inputs. And finally, one of the problems with the QP-based approaches is that they are myopic in nature. What it means is that we can guarantee that as long as the feasibility set is non-empty, the QP would have a solution. But can it guarantee that the feasibility set would not become empty in future time? That's not something that the QP can manage, because it only has the X variable at the current state. And it can only deal with that, right? So to deal with this non-emptiness of feasibility, we can adopt a multi-rate control framework, which we have started working with the Caltech group at where we are exploring a multi-rate control framework where we have an MPC problem at a high level which plans a trajectory such that the QP would remain feasible, and we solve the QP along, or rather with an objective of tracking this reference so that, the QP would not become infeasible in future. All right, so some brief conclusions for the second part, for the optimization. We designed what we call as fixed time gradient flows to solve the convex optimization problem within a fixed amount of time. We showed convergence under relaxed conditions, and we demonstrated numerically how we have improved performance as compared to the nominal schemes. Now, again, some very recent developments. We have extended the results to distributed setting in collaboration with Dr. Baranwal, and we have also extended the results to non-smooth optimization problem where the objective function is not continuously differentiable, along with the people mentioned below. All right, so some future work on the multi-agent control side. Even for the 4-agent case study for the robust control design that I presented, we chose the initial condition and the goal location in a way that the deadlock would not occur. Deadlock means when multiple agents come very close to each other and they cannot resolve their conflict and they just get stuck with each other, right? So what I would like to study is more systematic way of resolving deadlock. And there are basically two things that we can do. One is what we did for the case study, choose the initial condition and the goal location so that deadlock would not even occur. Other approach is we allow the initial condition and the goal locations to be arbitrary. And once the agents get stuck in a deadlock, we resolve them after we encounter them, all right? So it's an open problem in the literature, and that's something that's a very, very important class of problem for multi-agent control. And that's something that I would like to study in future. On the QP-based side, as I mentioned very briefly, we have already started working on zero-order whole controller for safety. But with the discretization preliminary result that I presented for fixed time stability also, I would like to study how we can extend the result with zero-order whole controller so that we can guarantee both safety and fixed time stability. Finally, on the robust control side, if you would recall, we used the worst case disturbance bound gamma in our Quadratic program, right? Which solves the problem, but basically it's the most conservative approach that one can take. So what we would like to do is basically use adaptation or learning-based approaches so that we can learn something about the disturbance. Here in this work, we assume that we do not know anything about disturbance, so it was very conservative. But if we can approximate the form of the disturbance, or if we can learn some distribution of it, then we can use that information to reduce the conservatism. And finally, what I envision doing with these fast control schemes and fast optimization scheme is basically utilize them in a safe online learning. So essentially, what we would like to do is basically relax all the assumptions. We would like to study systems whose dynamics is not known, and we would like to learn the environment, which is also unknown, while keeping safety. So that is something that we think we should be able to do using the fast optimization and fast controller schemes. All right. So with that, let me acknowledge a few things here. So first, I would like to start with acknowledging our sponsors, NASA and Air Force, who made my work possible. And I would like to acknowledge my advisor, Professor Panagu, who has helped me tremendously in the last 4.5 years. She has been really patient with me, and I learned a great deal from her in the last 4.5 years. So thank you so much for being the great advisor that you are. I would like to thank my collaborators and my dear friends, Dr. Gupta and Dr. Baranwal, who not only introduced me to the field of optimization, but also helped me understand some of the crucial topics, and they helped me with everything in last 2-3 years, be it with my postdoc application, with preparing the slides, and whatnot. Thank you so much for everything. I would like to thank my committee members, Professor Bernstein, Professor Kalmanowski, Professor Rose, for taking their time to read my thesis in detail, give my feedback, and in general to be on my committee. I would like to thank my collaborators, and I do not want to put a list because it's going to be a long list, but all of my collaborators who made this research possible. I would like to thank the DESK lab members. DESK is our lab, which stands for Distributed Autonomous Systems and Controls. And special thanks goes to James Yusevich and Vishnu Chipre, who have helped me a lot in the last 4 years. Thank you for all the useful discussions that we have had, which helped me in understanding those concepts and for everything else as well. I would like to thank aerospace staff, Denise Phelps, who has already retired, but she has been tremendous help to me, Thomas Griffin, David McLean, and numerous other people who work in the background and make people like us, PhD students, able to do their work very smoothly. So thank you so much. I would like to thank my parents, Kunal Garg and Anju Garg, who have made tremendous sacrifices so that I can be where I am today. And finally, I would like to thank my friends and family members for all their supports. Thank you, and I'm ready to take any questions now.